Hello everyone and welcome to another video. So today we are on to week 7 of our AE501 adventure. So let's just jump right over to the lecture outline to see what we're doing. So this week we are going to start our discussion into partial differential equations, or PDEs. So this first video is just a quick introduction to PDEs. We're going to see that they are different than ordinary differential equations, or ODEs, that we studied way back in week 2 and 3. PDEs provide literally another dimension of freedom or dimension of interest. So this is going to be a real fun topic. So this first video is just introducing what is a PDE, some general techniques, how to solve them, and then what I'd like to look at is how to go about and apply this to a very classical problem, and that's namely the one-dimensional wave equation. We're going to see that the motion of a one-dimensional wave is very well characterized with a fairly simple partial differential equation. So I'd like to take a look at a quick demonstration of the physical phenomena here. You can see this is a quick 4-minute video showing what we're talking about. Then we are going to go ahead and try to derive the partial differential equation that governs the 1D wave equation, which is that demonstration we just saw. So this will get us basically the governing partial differential equation, and then what we're going to have to do is we're going to have to go ahead and solve that partial differential equation. So I'd like to discuss how we're going to go about doing it for this particular class of partial differential equation. Now, what we're going to want to do after we go ahead and solve this, we're going to see that this is a fairly involved process. It's going to build on a lot of the things that we talked about earlier. In fact, it's going to build on things like ODEs. It's going to build on some Fourier series that we discussed in week 6. So as you can see, this is about a 2-hour discussion where there's a fair bit of mechanics going into it. So some things that I always feel help me, at least when I'm trying to understand some of these complicated situations, especially things where time is involved and the system evolves over time. We're going to want to maybe create some movies or some animation so we can see what's going on. So these two movies, or excuse me, these two lectures are talking about how to generate movies and animations of a somewhat complicated scenario in both MATLAB and Mathematica. So please check these two out. Basically, this material here is what's going to be needed to tackle the homework for this week, but I'd also like to get a little bit of a jump start on next week as well, because there's a fair chunk of material that we're going to need to get in next week. So we're going to take a look at a few of these, and this is really an extension of the partial differential equation idea. So earlier we looked at the 1D wave equation. I just want to look at a few other types of physical engineering and scientific scenarios that are governed by PDEs. Namely, in this case, we're going to look at heat transfer and what's known as the heat equation, and we're going to look at solving that in one dimension. So again, once you do the 1D wave equation, this heat equation is not going to be very much of a problem. So that being said, that's the roadmap of where we're going. Like I said, this is sort of a 2-week session where during week 8, next week, we are going to be looking at continuing partial differential equations, but here during week 7, I just want to introduce the idea and then mostly focus on this very classical problem of the 1D wave equation. Okay, so with that being said, let's jump over and take a gander at the homework. Alright, so here we are. I've brought up homework 7. Maybe what I will mention right off the bat is homework 7, it is still due in a little bit over 1 week. So even though we're going to spend 2 weeks talking about PDEs, homework 7 is still the standard schedule of you only have about 10 days to work on it. So just keep that in mind, that this homework, just spend a week on it, don't get behind. You're going to see it's actually not that bad. So what we're doing here, in fact, there's only one problem, although that being said, this problem is kind of involved. We're basically going to be looking at that 1D wave equation scenario that we're going to be extensively looking at in lecture. So it's pretty much just looking at a vibrating string, which is a 1D wave equation. That's what we're going to derive in the video. So I think once you watch the video right here, right, it's going to be fairly straightforward what's going on. This first part is just asking, if you watch the video at this particular timestamp, I make some arguments of why a particular part of the equation has to be greater than or equal to 0. I'd just like you to discuss this a little bit. So part A, don't overthink this. In fact, I think if you just watch the video, it should be fairly obvious what's going on here. Now, after that, let's actually look at a physical picture. Let's put some numbers to some of these constants and see what happens. So part B is saying, I'm going to give you a string with a certain length, a certain tension, and a certain linear density. That being said, once you're given this, you should be able to almost fully define what are known as the eigenfunctions of this particular PDE. And again, you watch the video and I illustrate what these eigenfunctions are It should be pretty straightforward. And in fact, speaking of illustrating them, that's exactly what I'm asking you to do in part B. I'm asking you to create an animation of the first 4 eigenfunctions using MATLAB, okay? And I'm going to make a note here. I'm explicitly calling out MATLAB. You have to use MATLAB to generate this. In a future homework, we're going to look at using Mathematica to generate these animations, but I would like to start off getting everyone comfortable making animations in MATLAB. I think it's a little bit easier to kind of step into. So again, part B is basically you're working to make an animation or a movie of this. And in fact, maybe what would be easy is I can just show you an example of what mine looked like so you can get a rough idea of what I'm actually asking for. Let me pull up the movie. It's on this other screen. Let me drag it up here. So this is effectively what I'm asking for part Bravo of this problem. And again, these eigenfunctions, it's going to make sense what they all are once you go ahead and watch the video. But this is the output product of part B. It's basically a series of animations that look something like this. Okay, great. That's that part B. Okay, so now part C is actually, this is where we're going to tie into some of our Fourier analysis that we talked about in week 6. So I would now like to think about combining a series of the eigenfunctions to get an arbitrary solution for an arbitrary initial condition or initial deflection of this string that we're describing here. So again, I have a picture of the guitar down here. And again, all we're asking for in part C is, let's assume that you go ahead and pluck the string like this. Like, so think about a guitar player. They're going to induce an initial condition on this string. This initial condition is described like this. And in fact, I kind of tried to sketch it for you here as this red kind of weird triangle that it's not, they're not picking it in the middle. They're plucking it closer here to the base of the guitar, not at the neck. So long story short, I describe it for you mathematically right here. This is what the initial condition or the initial deflection looks like. So what we're now asking for is if you were to deflect the string like this initially and then let it go, what's it going to do? And then just go ahead and make yourself another animation of this by taking several partial sums. And again, I'll let everyone kind of think about this a little bit. And once you dig into this, I think it's going to make sense what all these partial sums are talking about. Again, probably the easiest way, instead of sitting here talking about it, let me show you my animation. This is kind of what I'm expecting. Let me play that again and I'll put it on repeat. So yeah, this is all we're looking for. You can kind of see that, maybe if I can pause this correctly at the right time. Oh, crud. It's kind of difficult to pause. Well, you get the picture, right? That at higher levels of partial sums, you get a better approximation of the actual solution. And you can see that, yeah, we have this kind of triangular wave. And you can see that this triangular wave kind of just oscillates. So basically, this is the solution to this 1D wave equation PDE to the specific initial condition that I specify in this problem. Okay, so that's the output again of part B is an animation. Okay, now part D or part delta, I'd like to just modify this ever so slightly. What if instead of picking the guitar string and giving it this red initial condition, what if you give it the green initial condition? Does that change your answer? Does it change the sound? Does it change the, maybe let me just put it that way. I don't want to talk too much. Does it change anything? Like if you were to switch the initial condition, does this make a, does this have an effect on the overall solution? So that's what I'm asking for in part D in a little bit more complicated fashion, but at the very highest level, that's all we're asking for is if you have different initial conditions, what does it do? Okay, now part echo here is really just taking the animations from part B and part C. Those ones, I'd like you to now prove that you actually were able to create those animations. So part Bravo and part Charlie, you don't have to turn in anything for those parts because part Echo here involves taking those two animations, making a single movie, making sure it's smaller than 5 megabytes, and then uploading it to the website with a very specific name so that we can see it. Again, all I want to see is that you have an animation that you were able to successfully create a movie on your machine. So this week's homework, you actually have 2 deliverables. One is the PDF like always, right? You write all this up, you submit a single PDF. But now there's a second additional deliverable for this, and that's part E. where you need to combine your two movies into one. And again, let me just show you an example of mine. This is the deliverable for part E for my solution. It's just literally stitch those two movies together. The first part, show me the result from part Bravo, which is just the eigenfunctions here. This is what they look like. And then stitch it together with the triangular deflection here and play the two one behind the other. That's all I'm asking for. Just, however you want to combine those movies, that's totally great. There's lots of free programs out there. Another shameless plug, if you're interested, I do have a video on the channel showing how to use Blender for video editing. It's actually a very powerful free video editing and actually animation program, but I use it primarily for video editing. In fact, all of the videos that I put together on the channel are pretty much edited through Blender. So if you want, here's a link to show how to get Blender up and running and how to maybe use it for video editing. And again, all you're doing is taking the output of MATLAB, which should be an AVI file in part B, an AVI file in part C, and you're just going to combine them together into a single small video file and submit that to the Canvas site. Yeah, that's pretty much it. Okay, so then lastly, part F is, now that we have all of this discussion about the wave equation, and in fact for this guitar, I'm asking, what are these things? So don't overthink it. Tell me from a mathematical perspective, what do these things here at the neck of the guitar do, and why are they, what part of the math does this influence? And therefore, what part of the eigenfunctions, what part of the Fourier series, all that stuff. I think it's fun to stare at this from a kind of nerdy mathematical perspective and see what these things are doing. Okay, so that being said, I think that's pretty much homework 7 and week 7. Like I said, make sure that you know that this homework, it is still due in about 10 days, and there are 2 deliverables associated with this homework assignment. So obviously submit the PDF like usual through the Canvas site, but also you're going to have to make sure that you do submit your video file as well. So for every student, there should be 2 items that we are going to look at for grading this week. Okie dokie, that's pretty much it. I think this is probably a nice spot to leave it. I'll look forward to talking with everyone during office hours. Otherwise, we'll chat next week. All right, bye.